Welcome everyone to today's webinar. Whether you are a long-time DC fan or just getting started with DC, we're excited to have you here. So let's begin. Welcome to Unlocking Direct Current, HVAC, Solar and DC, the new energy trio for high-performance buildings with CurrentOS. Our hosts are Steve Connolly, CEO of Arriba Technologies, and 𝘂𝗵𝗵𝗆𝗍, President of CurrentOS. Arriba Tech is a valued partner of CurrentOS, and I am 𝘂𝗶𝗍𝗆𝗆, responsible for marketing activities. Before we dive in, just a few housekeeping notes. Feel free to ask any questions in the chat. We have set aside plenty of time after the presentation to address your questions and have a discussion. We are recording this webinar, so you will receive it by email, and you can also access it on LinkedIn. We will also share it on our LinkedIn page. And of course, yes, follow CurrentOS on LinkedIn, on YouTube. You can find a lot of content on YouTube. We have quite a few webinars now. We have a technical MOOC. We have some videos where we explain what CurrentOS does. So it's a great way to stay connected with our vibrant DC community.
Okay, so thank you, Raphael, and also thank you, Steve, for joining. So just as a reminder, because there are several people who are on their first call with us. So CurrentOS is a partnership, a global partnership of companies involved in direct current and low voltage direct current distribution. To date, we are 86 partners. We have new companies joining every week, I would say, more than every month. We are represented in 25 countries, and this partnership is made of companies making products, company making integration, and also academic certification bodies and trade groups. And so all together, we try to develop interoperability rules for DC, pilots to demonstrate the DC benefits. We communicate around these benefits, and we also try to provide the standardization bodies with some pre-work so that we can accelerate the standardization. So this is, in a nutshell, what CurrentOS is doing. And we can move to next slide. What is very important is to understand that we are learning by doing. We are not only on a theoretical research, or we are learning from real case projects and real use case. And I'm very happy and very proud, very honored that Steve is first one of our prominent partners and also helping us today with this webinar, because he will tell us about real cases that have been implemented in the UK with a DC grid that implement a lot of the rules that CurrentOS has described. A lot of DC actors are converging to similar approach. So I'm very happy to have Steve here to present one of the cases that is in this panorama of different cases. So thank you very much, Steve, and the floor is yours.
Okay, thank you, Yannick. Thank you, Raphael, and thank you to the audience for tuning in, either in your lunch break or at your breakfast time, depending where in the world you are. So I'm going to give a very wide-ranging presentation. I'm going to discuss engineering points and economic points and societal points to do with the green energy transition, because I think it's relevant to us getting an understanding of how DC electric systems are going to do what we want them to do, which is to make the world better, make our customers happier, and make profits for our shareholders. So I think there's a way that we can make everybody happy, but I'm also going to sound a note of caution. I'm going to say that there's also a way that we can drive this train off the tracks if we are not careful. So My company, I will start by telling you about my company and why we are doing what we are doing, and why I'm not surprised that the DC discussion is gaining speed and momentum around the world in the way that it is. I'm not surprised. So originally my company was involved in cooling technology, and like many cooling companies, we got to around the year 2010 and we saw the potential for heat, which is another form of cooling technology, funnily enough. So we started to make some heat pumps, and originally we wanted to be making small heat pumps for the household market. And we accidentally found ourselves getting into the power electronics business. And I'll tell you why that is. It's because a heat pump has within it a motor system to drive the compressor. Mostly it's the compressor we're concerned with. And to control the compressor, it's absolutely essential to be able to vary the speed of the compressor. And with small heat pumps, the only way you can do it is with pretty much custom-made variable frequency drives. Now, some people call them inverters, some people call them motor drives, but that's what they are, variable speed motor drives. So we accidentally, we started off by traversing from cooling into heating, and on that road, we accidentally found ourselves in the world of power electronics, and we didn't know anything about power electronics to begin with. So we spoke to a very friendly professor at our local university in Cambridge, and he agreed to help us. And so I will describe to you shortly what we've done with power electronics. And so I suppose the second accident is that we've now found ourselves in the DC microgrids business. Actually, when we started all of this, we just wanted to move DC power from solar into variable frequency drives, into battery systems, and we wanted to harmonize that or balance it with power top-up, if you like, coming from the AC power grid through rectifiers and similar devices. So by and large, we work with 700 volts of DC, and again, this is pretty much by accident, the same that Current OS is talking about for international standards. So I'm going to suggest to you that electric HVAC is the only kind of HVAC going forwards. We have to imagine that gas and oil-fired heating really is finished. Second, the heating and cooling part of electric HVAC is inevitably delivered from the same machine. We're not going to have one machine doing cooling and one machine doing heating. Third, the electric of electric HVAC is in large measure, or at least it will be, locally produced from the solar rooftop. Fourthly, much of the home produced solar electric that we speak of in this electric HVAC will be buffered for some hours. It won't be live. It's not going to come necessarily live from the solar into the HVAC system. It might go via a battery system for some hours. And then my fifth point is, and don't worry, I'm racing here, but we'll unpack this as we go through. Fifthly, these plants need more than a few timers and relays to make them work. They need a digital layer. So I've described to you why I think it makes sense for heating, ventilating, air conditioning, and solar, and the digital layer. And in buildings, we call this digital layer building management computing, or building energy management computing, BEMS. We think it makes sense for this to be co-engineered in some way. You'll hear me use this word co-engineering, and at the end I'll explain why I think it's quite important that we get our heads around this, even if we call it something different. So I'm going to expand these ideas and suggest to you that the electrical engineering part of co-engineering is almost certainly best carried out using some form of DC power transfer, a DC power transfer system. Now, if you want to call it a microgrid, a DC microgrid, that's fine by me, but I'm not necessarily hung up on the names. I remember the internet used to be called the information superhighway, and now we just call it the internet. So yeah, we call things a DC microgrid, and that might be the name. It might be the new internet style of name, or it might be that we just call these things DC power transfer systems. And why not? Because after all, solar is DC, electric motors inside HVAC machines are DC, or at least the frequency drives connected to those electric motors are DC. Battery storage is DC as well. And when I speak of battery storage, I'm very cognizant of the fact that batteries do also come on wheels. And at the moment, we speak of batteries on wheels in one subject, and then we speak of buildings in another, as if it were another subject. At the moment, that's as it is, but I'm open to the likelihood, I think it's a likelihood, that electric vehicles and buildings will become natural bedfellows, that they will give and take back electricity from one another. Can I have my next slide, please, Raphael? So these are the products that we make as a company. We do cooling, heating, batteries, solar, DC power transfer, and the digital layer that hangs it all together. So the software necessary for electric HVAC we do in-house, and we validate the performance of our equipment at system level before we ship anything. So we make dual temperature heat pump chillers. That's machines that do cooling and heating at the same time, or they're capable of doing it at the same time. We make two-pipe, what we call a two-pipe heat pump, which just does heating, or a two-pipe chiller, which just does cooling. We make packaged assemblies of variable frequency drives with DC to DC converter assemblies. The DC to DC converter assembly is our converter unit is the original one that we developed with Cambridge University Engineering Department some 10 years ago now. We've enhanced that design so that we can take up to 3 channels of solar simultaneously into a 20 kilowatt power converter, and each running its own PowerPoint tracking system. And we can push that then into a 700 volt DC bus, from which we can operate an array of other equipment, such as battery chargers or variable frequency drives. We also reluctantly at first got into the solar rooftop business. Obviously, there are lots of contractors who can do solar rooftops, but we only had one good one in our address book, lots of bad ones, one good one. And he got so busy he couldn't really take any more work. So we ended up doing that ourselves as well. And solar rooftops, by the way, I discovered it's actually tricky. It's not as easy as you might think. So you might say it's greedy for one company to have its finger in so many pies. And I can't disagree. There are days when I do indeed get a sense of indigestion when I look at all of the pies that our fingers are in. But really, this is about delivering high performance buildings. So the title of our presentation today is the energy trio for high performance buildings. And I think I'm standing on terra firma when I state that the building services that our company delivers are indeed in the high performance bracket. very carbon efficient, very financially efficient. If there was an easier way, I would take it. Can I have the next slide, please, Raphael? But it's sensible to check our ideas against the real world. So if I just zoom out of buildings and take a look at the wider picture, not just in an engineering context, but in a societal sense as well, then what we can see is 4.5 megatrends at play. And I'll explain where we get the half. So first of all, electric vehicles. The population of electric vehicle charging systems is growing by the day. I suspect that across Europe we must be close to 1 million chargers by now, if not more. Maybe somebody knows the number, they'll tell me. Solar is not just the story of the moment. I think it's the story of all time. It goes into my top 10 of inventions ever, like the bicycle and the sailing boat and those sorts of things. So if we just look at this slide down on the left of my image from the Global Solar Council, we can see that the quantity of solar that was installed between 2022 and 24 is the same as the quantity of solar that was installed in the 68 prior years. So we've now reached the point where we can do 68 years of work in 2 years, and it's accelerating. This is a big deal. The other big deal, it's a massive deal, is data center rollout. All over the place, we see these great big computing facilities gobbling up more and more amperage. And as the artificial intelligence thing gathers pace, the energy consumption will grow. Heat pumps. So the graph on the right, you see the growth there. These are McKinsey numbers, compound annual growth of heat pumps. I think the numbers might be an underestimate, actually. And within a heat pump, within every one of them, you have variable speed motors. And this is almost like 1.5 things going on here. We've got heat pumps and motors at the same time. Can I have another slide, please? So it's happening out there, and that's good from the point of view of we're all excited about the prospects to do more business and to further our engineering careers and to make our shareholders happy. But there's a but. There's a lot of engineers in our midst who are very worried about the speed at which we are going, and they have good reason to be worried. So right here you see a picture of an electric transformer in London which caught fire a few weeks ago. It was a pretty severe incident that knocked out Heathrow Airport for almost 24 hours. Almost for sure, even though the investigation is not published in the official domain, almost for sure this was caused by overloading. Apparently this transformer had been running at far in excess of its maximum nameplate for an extremely long time prior to this happening. And of course we should be aware that as transformers get old, the nameplate should be derated, not uprated. So can we have another slide, please? So the problem at hand is a complex one. We've got to balance things off, solar on the rooftop, cooling and heating machines working from the same machine room, battery storage. The title of this presentation is Solar, HVAC and Microgrids. 3 words. I think this is a complex problem, and we have to address the problem with some joined up thinking. So yes, we need DC power transfer systems, we need, and you can call it a microgrid, and we need solar systems, and we need digital systems and HVAC systems, battery storage systems, electric vehicle systems. So a system, I would argue for a systems level approach. Can I have another slide, please? And I'm not the only one. So I always think if I'm trying to reinvent the wheel, I've made a mistake. We really shouldn't go around reinventing the wheel. So the automotive industry has already gone quite a long way with this building blocks approach towards solving the problem of how you push DC power around the space. So there's an example in the top left of my image of a city bus working from a 700-volt DC battery system, powering up a multi-way inverter, which is in turn powering up air compressors, power steering, hydraulics, air conditioning, and other things. So my approach is pretty well to mimic that and to package it all up inside an easy-to-use system, and then indeed to bury it inside an HVAC plant, so that it's not scary to the blue-collar guy who has to do the maintenance on it. It's pre-validated. We know what the performance is. I'm reminded that it wasn't MS-DOS or the graphical user interface or the low emission monitor or modem or a PDA or a keyboard mouse that shot home computing into the stratosphere. It was co-engineering that lit the blue touch paper. Co-engineering brought us the iPhone. Everything all together, the Swiss Army knife of computing in your pocket. Have another slide, please. So pre-validated solutions made out of building blocks. What does that do? Well, for one, it makes it easy for the user. And in our case, in a building, the user or the person who touches the equipment is probably the user's maintenance guy. So he has to be on board. We've got to give him something that's reliable, easy to understand, not too many scary words or scary things that might happen to him if he puts his spanner in the wrong hole. So we get that, but there's a bigger picture, and it is what I would call green bonds. So I'm going to explain to you how this is interconnected. Believe you me, I am going to explain it. So these boring but steady workhorses of the financial system can move mountains. If you don't believe me, then maybe you would believe Donald Trump. He's a mountain, and he was moved by the bond markets just last week. The question I would like to pose, going back to my point about co-engineering and systems level problem solving, is whether the bond market can lend us a hand. And luckily for me, a number of highly educated have already done the maths on this. The answer is in, the answer is yes. So it's probably not an exaggeration to say that the energy transition needs green bonds just as much as it needs technology and engineering. There is a wall of money to pay for the greening of our built environment, but we have to deliver the real deal. We have to deliver systems that we know are going to work. Can I have the next slide, please? So green bonds, this is a check sheet from BNP Paribas. They're one of the biggest issuers of these instruments. You see there that they want certification, proof, safety track record. They need a paper trail. Bankers can collateralize all sorts of things, aeroplanes, buildings, but they can't collateralize fancy ideas. So we need to make sure that what we produce is measurable and repeatable. Bankers can collateralize wind, solar, but for them to really be able to collateralize the large-scale systems that we're talking about here, which is also the rollout of aerothermic and geothermic heat pumps and interconnected systems. The calculated payback on these engineering assets often is the calculations don't marry up with the reality, because You know, if we go and calculate, for example, a solar rooftop at pushing out electricity with a value of 25 cents per kilowatt hour, and if we actually push that power instead into the public grid, we're probably making 5 cents, not 25 cents. We're wrecking our investment, and we're wrecking our reputation with the bankers. So we need a digital layer that harmonizes or synchronizes solar self-consumption with solar production. Again, it's a question of system level thinking. Running low on time. Can I have another slide, please, Raphael? So I say that we can build hundreds of buildings, thousands of buildings using all of these technologies with a DC electric backbone, with solar, with interconnected cooling and heating systems. We can build them in a way that the end user's engineer is happy to go along with, that's reliable, that pays back, and that wins the trust of the green bond industry, so that we can repeat and repeat and grow using long-term financing. To collaborate, we need to bring together the experts from power electronics, HVAC, energy transfer and storage, building level computing, IoT, and finance. We must invite the finance guys into our conversation. That's pretty well my firm view. So can I have another slide, please, Raphael, and then I'll wrap up and we can do some questions. So here's two images of a train. The first one on the left is the happy train leaving the station. That's the green energy transition as looked at by a number of us. Unfortunately, amongst the number of people looking at that rosy picture, there is a percentage of what I would call the green washers, the guys who want it all to be great so that they can pocket the profit, but they don't want to do the heavy lifting. And I then would suggest to you that there's a real risk that this train is not a happy train if we don't do our mathematics and our engineering and our finance properly, that instead this train might derail. And if it derails, it's going to be really, really tricky to get it back on the rails. So I think the energy transition, just to wrap up now, it's a gigantic engineering challenge. It's absolutely not plain sailing in a political sense, neither at the level of an individual building, nor at the level of national politics. There's as we all know, there's a huge pushback against this green engineering, and we need to be really good at what we do so that we can win these people over. We're not going to force them out of the way. We've got to win their hearts and minds. Green bonds and green engineers are natural bedfellows. I'd like to put that view over there. Systems thinking is what's called for, and systems thinking is not just for techies. It means systems in the wide sense, including the financial sense. And then my word of the day, just remember this word, it's a good one, I think, is co-engineering. I would argue that co-engineering should be taught in schools even. And I even would suggest for all of us here something that ties our conversation together at the end. I would suggest that chapter 1 of the syllabus on the co-engineering program should be DC power transfer systems, solar, batteries, variable speed motor drives, LED lights, computers, you name it. So I'm not going to talk anymore, but I'd really be very happy to have a conversation with the folks out there if they haven't all gone to sleep or choked on their Weetabix or got stuck in the queue at the coffee shop or whatever it is. So Yannick and Raphael, I'll stop.
Yeah. And thank you very much, Steve. And maybe, well, one comment and one question. First, You obviously made some technical decision to make your system work before knowing CurrentOS rules. And the funny thing is you came out with very similar approach. Just another example that the rules that CurrentOS is promoting are not exotic thinking of crazy guys, but if you spend time on trying to make energy transition, trying to make power efficient system, trying to make the most of renewables, we will all come out to these rules, and CurrentOS is here to promote these rules. And I'm very happy that you, Steve, are part of our community to help us to move it forward. But maybe could you, to complement your presentation, your excellent presentation, could you say a few words about concrete example of system you have delivered and implemented with thanks to these principles? Because we have seen pictures of your switchboards, and it's not mock-ups, it's really product, it's really installations. Can you say a few words about it?
Yes, so I can share a link after this, which was written up in one of the solar magazines, showcasing a job that we did for a hospital in Cambridge last year. In fact, that job was it was a prize winner at the European Heat Pump Awards last year as well. And in that installation, we've got some very, very innovative joined up cooling and heating machines running from a mixture of solar power through our own DC to DC converters, and also operating with some pretty different type of building management software. So I don't like to reinvent the wheel, but sometimes I have to. The software for that particular job, we made it ourselves, because none of the software vendors in the BMS, BEMS marketplace have a product that can run simultaneous cooling and heating in a balanced fashion in a way that synchronizes with solar. So we want our machinery to do the heavy lifting while the sun is shining the strongest, and to do the least amount of lifting while the sun is not shining. So I will send a link that you can circulate at the end, and there's a very good write-up, as I say, in this solar magazine that describes some of what we do.
Can you, well, and probably it will answer the question of Wilfried, can you give some figures about the power of these heat pumps and the heating power or cooling power you implemented?
Yeah, so that was the biggest job that we've done. We have, if I speak of electrical kilowatts, we have 80 kilowatts of solar. Total electrical installed power is 250 kilowatts, but normally speaking, the system will operate happily with 80 kilowatts. So in the sunny weather in the summer, when we're providing cooling and heating into this hospital building, we do get several hours every day where I call it freewheeling. We go freewheeling. We're off the grid for several hours every day, and we're running all of the ventilation and cooling and heating in a mid-sized hospital building with 3 operating theatres and 50 recovery beds. And this is in England. You know, we're pretty far north. So I'm absolutely sure that as an industry, we're not really doing any more than scratching the surface of what's possible with DC power and solar when it's coupled together in an efficient way. Yeah, so we have an installation there. It's working beyond everybody's expectations, and that's in England. We have a lot of clouds, and we're far north. So the possibilities for running refrigeration machines, for example, in say Arizona or Florida or Brazil, Australia, it's completely feasible to run a complete supermarket. For example, supermarkets are good because they have these large flat roofs. I would stick my neck out and I'd say at least 100 days a year freewheeling, at least. So there's lots, and DC power, of course, is the big thing there, because it just it gives you 7-8% improvement over conversion losses. You harmonize that with some digital synchronization of machinery and solar, and straight away you've got a system that is giving a real world solar yield 20-30% bigger than what you'll get with an uncoordinated system. So the finance guys, they love that.
And what are the biggest obstacles you faced in implementing this kind of systems?
Well, it won't surprise you if I say politics. There's a lot of people in this world whose job it is to say no. And this is why in my presentation I was careful to say that we must win hearts and minds. Now, you have to understand we now have a number of implementations in the field, and it's kind of getting easier. We can say, well, it's the same as this one, so and that's now validated. But you need to win hearts and minds. There's a lot of very cautious people out there, sometimes for good engineering reasons, sometimes for reasons that are a little bit beyond me, but maybe they're worried about their job security. But yes, so that's the real barrier. The barriers are not technical. They are not technical. And I do believe that if this is done properly, the barriers do not have to be financial either. This is a momentum play. I think it's a snowball at the top of the mountain as it goes down the mountain and gathers up momentum. It's unstoppable in my view, because there's nothing else that can compete with it financially or in carbon terms, and so it has to be the way.
Very good. But when I usually ask this question, I get answered, well, in DC, there are no products, there are no standards, there are no knowledge. So you have the products, you have the knowledge. Apparently, you went around the standard issues. So that's just great.
Yeah, no, the barriers are not engineering, and I would argue that very strongly with anybody who says that there are engineering barriers. There are none, absolutely none. There might be an attitudinal barrier, and we have to take that very, very seriously. But there's not an engineering barrier.
There is also a question about the cost analysis. How far do you have published something about your cost comparison or the benefits of your installation, including compared to an AC system?
Well, we have relatively a small number of implementations. We have 7 or 8 implementations in the field, and I don't feel it's my job to reveal too many of my commercial secrets right now, but I'm happy and my customers are happy. There is a piece of work which is being done by Warwick University in the UK, which is going to be published, we think, at the back end of 2026, which is looking at DC microgrid technologies in the British healthcare system, and that will actually provide some independent analysis and independent, sort of independently validated views on this. But certainly from where I stand, I'm happy with the results, and my customers are happy with the results, and my shareholders are happy with the results. And without being disrespectful to anybody, you have to appreciate that a lot of this is my commercial secret, so I'm not going to tell you how I bake my cake. It's got my own ingredients in it.
But I guess when you sell this DC system, you don't sell comparison apple to apple with an AC system. It's an overall package or an overall service you provide, right?
Yes, I mean we've got some. Let me be a little bit more frank. we're in a market which is changing, and like with all markets, there are the front runners, you know, the early adopters. We're still in an early adopter market, and realistically, our customers, they tend to be universities, hospitals, laboratories. Funnily enough, we don't have any financial institutions as customers, but I think also they are, you know, they're front running some of this. So we're not in a mainstream market just yet, and mainstream market rules kind of don't apply at the minute. We're in a, you know, an early adopter market, but that early adopter market by itself is big.
Yeah, sure. Shall I continue to read the question in the chat, or we
Yes.
open the mic to people who want to raise their own questions? Maybe who want to ask a question? I can continue to read, but maybe is it Ritu? You have a question, you want to ask it? Yeah, unmute your mic and go ahead, please.
Especially with the solutions that you're bringing to the market. I don't know if I'm audible at all.
Yes, you are.
Yes,
We hear you.
I
Yes.
can hear you.
And we
Okay,
can see you.
Perfect. So thanks, Lee, for your presentation. It was quite intriguing. Following my question on the total expenditure analysis, I'm quite curious because on the protection schemes and devices, you've mentioned the microgrid controller. So is that a part of the offer that is provided by like Arriba Tech, or is it something which is separate and that comes from your collaborators or your partners?
No, that's in-house. So we have, and again, we don't call it droop control, but we have something which is more or less a droop control, which shares power between DC to DC converters and variable frequency drives, and that's our own firmware, which runs at chip level inside the power electronics.
Okay, and that is also responsible for the protection.
Yes, we have to follow various rules for solar implementations, and we do have various checkers that are going on, running in the background, which can disconnect equipment at quite high speed if we have to.
Mm-hmm. Well, thanks.
Questions?
I just have a follow-up question to what we just discussed. So these protection schemes that you mentioned, which are inbuilt in the firmware, protecting the CurrentOS standards, right?
Do they comply with CurrentOS standards?
Exactly. That's my question.
They predate CurrentOS standards, and if I would have to check back with you, but I think that if they don't sit exactly in alignment with CurrentOS standards, then I would think that they are either more stringent or nearly as stringent. But you know, you have to remember that we predate CurrentOS.
Yeah, if I can generalize, this is exactly how CurrentOS works. You have seen a lot of projects that has been done, and the existing version of the rules of CurrentOS are the learning from these pilots, all these pilots. So obviously, the rules that we have written today are, I would say, later done, and then the pilots are all a bit, let's say, older version. That's the way you learn from real case. Huh? Otherwise, you make 10 years of paperwork, and then you start to witness that it doesn't work. So we make it work, and we improve the rules.
Interesting. Thanks, Yannick. Thanks, Steve.
We had a question about regulations that you had to follow. I don't know if it's about heat pump regulations or.
What is the question?
About regulations worldwide. Maybe Nilo, you can complement your question or elaborate.
There are, and I probably need to lean on my engineering director for better quality answers than the ones I'm going to give. But we are governed by various Euro norms and British standards concerning solar power conversion, electromagnetic noise from power converters, various norms to do with the mechanical engineering that we're involved with as well, and of course electrical engineering norms. And so yes, we are governed by all of that, and we do take a cautious approach. Some of what we have done has caused us problems because it's difficult to implement, and sometimes you really wonder, is it totally necessary? But it is there. So yeah, the legislative background is there for a good reason. It does a good job, and we try to stay in accordance with it. We don't want to take a shortcut and land ourselves in court for having broken some rule. We don't want to do that.
Wilfried, do you want to raise your question directly? Wilfried, are you connected?
Yes,
Good,
I was
good,
muted. So thank you. It was very interesting. I'm from the Netherlands, and in the Netherlands we're facing net congestion, and we're also looking for heat pumps for working on our DC. I'm from DC Systems, and the question that I got from my customers is, what is the power gain that you have? Do you need less power to have the same heat output, and what is the efficiency gain? So so that will be put also into costs. And so how can I convince my customers to choose a DC heat pump in general?
Okay, so I don't think that your customer will buy just a DC heat pump. He's buying solar as well, and maybe some batteries too. And so if you were to put the question in a different way, if you were to say, what's the advantage of having solarization across a DC system straight into the heat pump? Well, the short answer is 7-8% by saving power losses. The slightly longer answer is at least double, if not treble, that percentage if you take account of the ability to synchronize machinery so that it does most of its heavy lifting while the sun is shining. What that means is, and you have to bear in mind as well that HVAC machines, heat pumps, they are power hungry. They take in most kinds of building, they are the ones that are taking the big amps. So if you get that bit of engineering in the bag, then you've solved a lot of the problem. And so you will get a better financial yield off your solar if you're self-consuming it in a meaningful way, not a silly way, but in a meaningful way, rather than pushing it backwards onto the grid. And indeed, I think in Holland, in some places, it's quite difficult to even push solar into the grid. So there's the answer. It's 7%, in strict DC terms, but it's probably 3 times that if he implements some of the tricks of the trade, which is to synchronize solar production and solar consumption.
Thank you. Very clear. I've just another question, if I may. Yannick, do you have tools for sizing installations? So you can predict the cost and the outcomes for installations?
Sorry, that was a question for me or a question for Yannick?
Yes. Sorry, there was a question for you, Steve. Thanks.
Oh, I beg your pardon. Do I have tools for sizing? We should have them. We don't. So at the minute, we're selling these systems directly to the customer. We are presently working on setting up some, a sort of a network or a collection of value-added resellers. And part and parcel of that is that we will provide a comprehensive tool set to the reseller partners that we go forwards with. So if you want to have a discussion about that, then we'll have that discussion separately from this meeting, Wilfred. I know that in Holland there are some good opportunities, and I have an affinity with Holland. I lived there for 2 years in the 90s, and in fact my daughter she wasn't born in Holland, but she was made in Holland. She has a Dutch name. My daughter is Saskia, so I have a very strong affinity.
Good, thank you. We'll catch up with you later.
Any other questions from the audience, guys? Everything's clear? Anyway, we will remain at your open to any more questions. Maybe, Raphael, we can just now show the last slide just to remind everyone that, as you see, CurrentOS is a living community, and we can welcome your company as a new partner, and you can also look at our beautiful new website, currentos.org. You can ask for questions at info@currentos.org, and we can continue to work together and grow the DC solutions and help the energy transition together. So this was my last message. Steve, do you want to have a last word, or Raphael a last word?
Steve,
I just want to say thank you to CurrentOS for working so hard behind the scenes to build the momentum on this. I'm very committed personally, and I think that buildings need DC. It's as simple as that. I think that we are a short number of years away from it becoming the totally normal way of doing things.
Great. And my last word will be stay tuned for our upcoming webinars. The next one, it's a preview information. It will be on May 22, about the same time, and it will be on the topic of cybersecurity with DC. Thank you, everyone. Thank you to both our hosts, and thank you to all our attendants. We will share the recording very soon, and see you soon.
Okay, thanks everybody.
Thank you, everyone.
Bye-bye.
Goodbye. Bye-bye.
Bye-bye. Bye-bye.